Acid-base balance and being able to interpret the results is one of the most important skills a respiratory therapist will have to learn. So as we learned last lesson, carbon dioxide is transported both in the plasma as well as on red blood cells. When we measure the carbon dioxide level as we take an arterial blood gas, it'll come up as the PaCO2, and this is measuring the amount of dissolved carbon dioxide in the blood. So although it's a small portion of the transport of carbon dioxide, because as we learned, most of it is transported as bicarbonate, it's a good snapshot of the amount or the content in our bodies. So as I said, carbon dioxide is mainly transported in the red blood cells, attached to or converted to bicarbonate. And so that way, the majority of the carbon dioxide that travels to the lungs is converted to bicarbonate, and then it goes through the reverse hydrolysis equation at the alveolar capillary membrane. That's where carbon dioxide is released and then ventilated out of our bodies. It's a good depiction of that. So when we talk about acid-base balance, we have to think of, first of all, what is an electrolyte? So an electrolyte is an element or a compound that when dissolved in water, it actually disassociates into ions, and they actually have an electrical current. So that's cations that have a positive charge to them and anions that have a negative charge to them. Then we have to think about a buffer, and that is a substance that is capable of neutralizing both acids and bases without causing sharp changes in the pH of a solution. In the solution of our blood, we need to be in a very strict limit between 7.35 and between 7.45 in order for our body to maintain homeostasis. So if you can look at the pH scale, it goes between 1 and 14, 1 being extremely acidic and 14 being extremely basic. So we live in the 7 range, 7.35 to 7.45. So if you want to think of one number, 7.40 is neutral for our blood. So an acid is a hydrogen ion donor to another substance. So it's capable of donating its hydrogen ions. So therefore it has a lower pH than 7. A strong acid is an acid that dissociates completely into hydrogen ions and an ion, a negatively charged ion. So an example of a strong acid would be hydrochloric acid. A weak acid is an acid that dissociates only partially into ions. Carbonic acid, which is the intermediary of the hydrolysis equation, is a weak acid that plays a big role with carbon dioxide transport in our bodies. A base is a substance that can accept or steal a hydrogen ion, as well as it can donate hydroxide ions in specific situations. A strong base, it completely disassociates, and that would be something like sodium hydroxide, where a weak base would be something that partially disassociates, and that would be like an ammonia. So pH in our body is maintained by the buffer system of both the blood and tissues, meaning the respiratory system and its ability to eliminate carbon dioxide, and the renal system and its ability to both excrete hydrogen ions and reabsorb bicarbonate ions when necessary. So those two systems work together to keep our blood pH within a very limited range. So the ability of an acid-base mixture to resist large changes in pH, it's called its buffer action. So we can see here with the hydrolysis equation, when carbon dioxide mixes with water like it does in our bodies, it is converted then to carbonic acid, which is a weak acid, which disassociates into both a base bicarbonate, and hydrogen ions. So therefore, the carbonic acid works as an acid in our body, and the bicarbonate ion works as a base in our body. So now we're going to look at something called the Henderson-Hasselbach equation. And just for some vocab terms, the pK is the dissociation constant, and that is where hydrogen ions want to jump off of the specific molecule. And here in the Henderson-Hasselbach, when we're talking about blood pH, it's going to be a constant, and that number is going to be 6.1, which is the dissociation constant of water. And then PaCO2 is the partial pressure of carbon dioxide in arterial blood. So that's taken from an arterial blood gas, and what that is the dissolved portion of carbon dioxide. We also get our pH and our PaO2 in that same way. The solubility coefficient of carbon dioxide, which we talked about in the chapters of diffusion, is 0.03. So therefore, our equation is pK plus log function of bicarbonate over our carbonic acid. So it's the pH equals the pK plus the log function of our base over our acid. So when you do this, and when we put in our values, in order to get a carbonic acid, once again, that's just carbon dioxide when it's mixed with water. And so what we have to do is assume that carbonic acid level is our PaCO2 times the solubility coefficient of PaCO2. And there is about a 20-to-1 ratio between base and acid in our blood. And so when we put in all of our values, it's pH equals 6.1, the dissociation constant, plus the log function of our normal bicarbonate level 24 over 1.2, which is our PaCO2 times its solubility coefficient. And when we put that into our calculators, we should get 7.4 as the pH level. So normal values when we're looking at arterial blood gases, the pH will be in a range of 7.35 to 7.45, normal being 7.40. And this will tell us our acid-base status of our patient. The PaCO2 is between 35 and 45, normal being 40. This talks about our respiratory status and how ventilation, effective ventilation is. The bicarbonate is between 22 and 26 milliequivalents per liter, and this is depicting our metabolic system. We can get our PaO2, which is our oxygen level in our body, and we can see if our patient is experiencing any hypoxemia. So 80 to 100 torr is normal. And then we look at our base excess, which we have between -2 and +2. And this is also indicating that our metabolic system is functioning. And it's the amount of hydrogen ions needed to neutralize the solution. So it follows very consistently with our bicarbonate levels. So different acid-base disorders that we will encounter are respiratory acidosis, respiratory alkalosis, and then a mixed or combined acidosis, which is both respiratory and metabolic. We'll look at a metabolic acidosis, a metabolic alkalosis, and then a mixed or a combined respiratory and metabolic alkalosis. So here's just a little example of a patient with respiratory alkalosis, usually from hyperventilating, where a respiratory acidosis is generally from hypoventilation. So then our compensation is the other system, either being our metabolic system, so the kidney's ability to keep or excrete hydrogen ions and bicarbonate ions, or the respiratory system's ability to ventilate faster and deeper or slower and more shallow. The more minute ventilation our patient has, the lower our carbon dioxide level will be maintained. So once again, a review on oxygenation. PaO2 normal is 80 to 100. 60 to 79 torr is considered mild hypoxemia. 40 to 59 is considered moderate hypoxemia, and less than 40 torr is severe hypoxemia. So when we're looking at arterial blood gas analysis, the first thing we want to do is look at our pH to determine, is it an acidotic or is it an alkalotic blood sample? Then we'll look at our PaCO2 and our bicarbonate to determine, is the etiology of the acid-base disorder either respiratory or metabolic, meaning is the PaCO2 or the bicarbonate levels out of range, pushing that pH level out of range. Then we'll look if there's any compensation to determine if the PaCO2 and the bicarbonate are changing in the opposite direction of the pH change to try and neutralize it. We can have either partial compensation or full compensation or no compensation. And then finally, we will classify our oxygenation status based on the PaO2 value given.